anything like this with a base which is a number is an exponential function with some restrictions for the base. If you remember, the base can be a number greater than 1, not 1, or there is one more option in which the base is between 0 and 1, not 1, not 0, and never negative. Then all these conditions given, only then this is called an exponential function. We've covered this in the previous class. Do you remember? There are two very important exponential functions. This one and this one. When the base is e, this is called natural exponential function. When the base is 10, this is called common exponential function. Why are they so important? And you can say, well, I have a sophisticated calculator that will perform any calculation with any base, whatever. That's fine, yes. When we get to log, that you can say. But why are they so important? Here's why. See here 10 to the x. See here e to the x. They have a special key. So, but you have to activate the second button. Second 10 to the x, second e to the x. Okay? So, if I want to determine 10 to power 4, I will not use the calculator, but if you want to, you get 10,000. If you want to use the calculator, and you have to on this, let's say e squared. Oops. See, that's why I don't like the software. Okay, e squared is this. Why? Because e, if you just want e, it's right here under the division. The same, it shares the same with key with the division symbol. Then you have 2.71 and so on and so forth. I just read about someone who memorized like 400 digits. Of e. Good memory, I guess. Now, let's take a look at the two possibilities, and because there are two different graphs. If the base is greater than 1, for example, let's say f of x equals 2 to the x, the graph will have a certain shape. For the other situation, let's say f of x equals 1/2 to the x, the graph will have a different shape. So let's take a look quickly at 2 to the x. This is a friendly function, which means the domain is, I can replace x by anything I want, positive, negative, or 0. So therefore, the domain is all real numbers. This is a friendly function. And when we graph it, do you remember how to graph this, or do I have to show step by step? Do we remember this graph? It's okay if you say no. Okay, very good. So let's look at x, domain negative infinity to infinity, and f of x. And let's pick some numbers. I'm going to pick -2, -1, 0, 1, and 2. Can anyone give us the function value when x is -2? Careful. So e to 2 to -2 is 1/2 squared, which is 1/4. So we plug in -2 in here, so we get 2 to -2, which becomes 1/2 squared, which equals 1/4. Agreed? Very good. So then what happens when x is -1? Let's plug in -1 and see what we get. Perfect. Let's plug in 0 and see what we get. Careful. Any number raised to 0 is? Perfect. And let's plug in 1. And let's plug in 2. Good. So now I would like to come up with the end behavior. I want to see what happens here, and I want to see what happens here. And you can say, find the limit. Okay, but I don't know limits yet. I do know limits, but we have to graph the function first, so you remember that. Or we can just write limit of 2 to the x as x approaches negative infinity, because that's going to be this limit, and limit of 2 to the x as x approaches infinity. Why not? Let's do that. So let's start with the right-hand side. So if this goes to 4, from 4 to 8 to 16 to 32 to infinity, where do you think this goes? Absolutely, there is no doubt. Excellent. So this is infinity. Let's go to the other side. Now this is a different story, right? Because I have the same situation when this is negative infinity. So this is 1 over 2 to infinity. But 2 to infinity approaches. So how much is 1 over infinity? Meaning I have a cake and I want to share it with everyone on the planet. When I knock on your door, how much will be left? If I start, let's say, in India. Nothing. So that's why this is 0. Because it's 1 over infinity. Now we know something about this. When x approaches negative infinity or positive infinity and the function values approach a number, this is called
domain.
It's called a horizontal asymptote. Exactly. Y equals 0, horizontal asymptote at negative infinity only. At negative infinity only. Is it at positive infinity too? No?
No.
No? Good. So then we are ready to graph this function when the base is greater than 1. So let's graph it, and we have to commit it to memory. So from left to right, -2 1/4. -1 1/2. 0 1. 1 2. And so on and so forth. Remember, I have to graph the asymptotes first. There is an asymptote, horizontal one, at y equals 0. So this is 2 to the x. What can you say about this function? Is it increasing on its domain?
Yeah, no.
Increasing, right? So when we talk about increasing, we say what happens to the y values as x goes from left to right. As x goes from negative infinity to infinity, this function always, which means that its derivative will always be positive, right? Because the slope at any point in time will be a positive slope, right? So its derivative would be positive. Let's talk about its derivative right here, right now. No, I would like to graph the other function first, because there is more to it. Okay, any questions on this? Any questions? Okay, we also have the other alternative, which is 1/2 to the x. Do we remember the graph, or we have to do the same thing? Okay, let's do the same thing. So then f of x equals 1/2 to the x. Can anyone give us the range of this function? 0 to infinity. Look at the graph, right? From the lowest y value, which is not attained, that's why it's in parentheses, to the largest y value. Good? Perfect. So let's do the same thing, negative infinity to infinity and f of x, -2, -1, 0, 1, and 2. When you're ready, please give me those numbers. When we plug in -2, remember you have to flip, right? 1/2 raised to -2 is 1/1/2 squared, which is 1/1/4, which is very good. 4 indeed. Okay, what about -1? Perfect. What about 0?
1.
Excellent. What about 1?
1/2.
What about 2?
1/4.
Excellent. So again, we want to go this way, left and right. Say it again. Yes, correct. So let's find the limit of 1/2 to the x as x approaches -infinity for this number or whatever that is. And the other one, limit of 1/2 to the x as x approaches infinity for this. So let's start with this one. 1/2, you can think in terms of 1 divided by 2 to the x, because 1 to the x is still 1. So the denominator has 2 to the x. So when x approaches infinity, 2 to the x will approach
0.
Infinity, right? And then 1/infinity will approach 0. I agree. So this is 0. What does this mean about the function? What does it say about the function? When x approaches infinity, the function values approach 0. Y equals 0, horizontal asymptote at infinity only. Let's try this one. When x is negative, or x approaches -infinity, I have to flip this. It's 1/2, right? It's going to be 2 to infinity. What will that go? Where will that go? Careful, let's do this together. So 1/2 raised to x is the same with this. So when x approaches -infinity, let's say I shouldn't be writing the way I'm writing it, but that's okay. This changes into 2 to infinity, which will definitely approach infinity. So then this is infinity, and that is infinity as well. So now we're ready to graph this function. From left to right, -2, 4 is this point. -1, 2 is this point. 0, 1 is this point, and so on and so forth. And of course, y equals 0, horizontal asymptote at infinity only. What can you say about this function? Is it increasing or decreasing on all its domain?
Decreasing.
Right, so that means that its derivative will have to be
Negative.
perfect at all times. Will it have a critical number? No, it's decreasing all the time or increasing all the time. It will not have a critical number, and it will not have a max or min. However, I have to correct myself. There are functions that have critical numbers when they always decrease or increase, but they will not be max min. Good. Okay, so now let's look at derivatives of these exponential functions. And let's start with the nicest one, e to the x. And then I would like to discuss f of x equals a to the x. And then function composition, which is e to a function of x prime, and then a to a function of x prime.
That's a u.
U, a function that is u of x. It's not u times x, it's a function of x. So what is the difference between these two situations? Here I have plain base function like here, but the exponent is plain x. This one could be x squared minus 5x. Here the base is anything but e. It can be 2, 1/2, 1/4, 1/9, 9, 10,000. But not e. So it's a different function. Shape pretty similar. Yes?
Do the rules still apply where it would be x times e and then to the x minus 1? Does it still apply?
We haven't discussed logs yet.
Okay.
We only looked at the exponential functions. In the next section, we'll talk about log.
Okay.
Yes, of course. You're way ahead of me, which is awesome. Okay, so first let's differentiate these. Now, I recommend let's look at either graphing them to see what the limit is, what the derivative is, if you would like, for a particular value, or better, what I recommend is to prove one of them. And the easiest one to prove is e to the x. Let's prove one of them. Okay, let's prove it. I'm not going to ask you to prove them, but I just don't want to give the final answer of e to the x prime without showing you what it is. Okay, so let's just prove e to the x. So f of x is e to the x if I want to determine f prime. Does anyone remember the long definition? It's the limit when h approaches 0 from f of x plus h minus f of x over h. This is the definition of the derivative. Remember, we had this on the first test. Please redo your tests, this one and the next one and the next one, every weekend. So you don't have to cram in everything 5 minutes before the final exam, please. So this is the definition of the derivative. We worked on this. This is the difference quotient, and the limit of the difference quotient is the definition of the derivative. So now what I want to do is create this for this function. So we see what it is. So f prime of x equals limit as h approaches 0. And now please tell me what to write. We are working with this function to find the difference quotient and the limit, of course. How will I write this piece for this function? Very good. Minus? Very good. Divided by h, of course. Perfect. So now I'm looking at this piece. And I just want to make a side note. Let's say a to x multiplied by a to y. You will copy the base, and what will you do with the exponents? Very good. But now I want to go backwards. And I wanted to use the backwards method for this, and tell me what to write. Excellent. Okay, look at this expression and say, I know what you're going to do next, and I will probably do it. But don't say jump from the Empire State Building.
Cross out the e to the x.
Factor out.
Yeah.
Yes, I agree. Limit as h approaches 0, e to the x. What is left in parentheses?
E to the x.
Very good. We have two terms. We have to have two terms in parentheses. Now notice, and I'm going to ask you, where does e to the x go when h approaches 0? E to the x. There is no h in it. So since this is a constant, I'm going to take it in front. I'm allowed to. It's a constant. It doesn't depend on h. So then this is e to the x, limit, h approaches 0, e to the h minus 1 divided by h.
Hold on. You said as a constant. What?
H approaches 0. It does not have an h in it. It's like 3. It's like 3 or 4 or 10. It doesn't depend on h. I can take it outside. Okay. After we finish this, I will show you a method. But we have to finish it, and then I'll show you the simple way. Okay. So let's go to the calculator.
I just had a quick question.
Yes.
Why is the e to the h in front of the limit? Can't we put limit h of 0 e to the x and then do the
Say it again.
Do you know how we pulled e to the x out? Why did we put it in front of limit h to the 0? We can't do limit h as it approaches 0, e to the x.
Sure.
Oh, we could do the other.
Yes.
Okay.
It doesn't matter. But it's like having 3 here, right? You can put it in front, or because it's a factor.
Okay.
You can take it already outside. It doesn't depend on h.
Okay.
If this were x approaches 0, I could have not done that because there is x in it. But this is h approaches 0. It's a constant. Since anything that is not depending on h, it will be a constant. Now you can keep it, we can keep it inside. Let me write it inside because it's the same thing.
I was just curious.
No, it's absolutely the same thing. It doesn't affect anything. What I want to show is find a number for this. And we don't have the tool that I'm going to show you in a minute. So that's why we have to do it with a calculator. So in y equals, please plug in, clear everything you have, and plug in just that function without e to the x. But there is no h in the calculator. So parentheses for the top, e to the x minus 1 divided by x. So what is this? It's that piece that I circled, e to the h minus 1 over h. But I can't put h in the calculator. So that's why I have to use x. So I'm trying to estimate this. When x approaches 0 from either side, when x approaches 0 from either side. So I'm going to put in negative 0.5 and then 0.5 and then get closer and closer to 0 from either side, and let's see what we get. So second in table. So I'm going to say negative 0.5 and then negative 0.2 and then negative 0.1 and then negative 0.000001, and then on the other side 0.5 and then 0.4 and then 0.2 and then 0.1 and then 0.000001. And now I want you to tell me what is the limit of e to the x minus 1 over x.
1.
So that's awesome. So this is 1. So what is the derivative of e to the x equal to?
1.
E to the x. So this is a very special function. Isn't it nice? The derivative of e to the x is
E to the x.
e to the x. It's not going to happen again. So enjoy it. So e to the x prime is e to the x. But now, yes?
E to the double x, the same thing?
When you say e to 2x?
No, e to like the second derivative. Yeah, the second derivative.
Yes. Yes, because you have to differentiate the first derivative. It will always be e to the x whatever. Correct. But now I'm asking you this. So we know the answer to this. I want to jump to this because you know the answer, because you know the chain rule. So now I want e to a function of x prime. What will that equal to? My markers are getting dry. Okay, so let's talk about this to refresh your memory. If I differentiate x to the third, I get 3x squared. Agreed?
Mm-hmm.
But what if I differentiate a function to the third power prime? What do I get now? Yes, I'm ready. 3, the function squared times the function. Excellent. So you know the answer to this then. Same idea. What is it?
Times u
e to u, it has to be e to u. Just e alone doesn't make any sense, right? It's just a constant. E to u times
E to x.
times.
Function parameter.
Exactly. That's it. So if I have just, remember here I should have written times x prime, times this prime, but what is x prime? Well, that's why we don't. So let me give you a couple of examples, and then we move on to the other one. So on page, I'll let you choose in a second. On page 304, let's practice this. From 11 through 54. I will choose first, 36. F of x equals x squared plus 3x minus 9 times e to the x. Okay, what do you recommend we do here? We want to find f prime, of course. Find f prime. What do we have to use? We have to use the product rule. Very good. It's a product of two functions. Awesome. Function 1 times function 2. Awesome. Thank you. So this is 1. This is 2. So then f prime of x. 1 prime. What do we write?
2x.
Excellent. Times the second one plus. I copy the first one times the second one prime. But that is the nicest function of all.
E to the x.
E to the x. Let's factor out e to the x and simplify the inside. So we have an x squared. We have a 5x and minus 9. And this is how we differentiate anything that has e to the x in it. X squared plus 5x. Oh, minus 6, minus 6, minus 6. Sorry, sorry, sorry. Negative 9 plus 3. I forgot about 3. Sorry, my apologies. Okay, let's look now at something else, like
Those two Roman numeral numbers you had over X,
this is function 1 and this is function 2.
Okay,
Yeah, so it only says that function 1 prime times function 2 plus function 1 times function 2 prime. Is that okay? Should I write the product rule? Okay. Very good. So let's look at 40. On the same page, 304. We have f of x equals e to negative x squared plus 7x. We're asked to find f prime of x. This is not plain x. It's not e to the x. It's e raised to a function. The function is negative x squared plus 7x. Any suggestions? We want the derivative of this. How do I write it?
E raised to negative x squared plus 7x times negative 2x plus 7.
That's it. Done. Any questions? I'm looking to see if they, yes, they do. They do talk about it. I was just making sure that they do talk about the other one. So we haven't finished. We know two formulas right now. We know how to differentiate e to the x, and we know how to differentiate e raised to a function. Now let's see what happens when the base is not a. It is not e, but a. So like, for example, what we had before when we graphed like 2 to the x, or we graphed 1/2 to the x. This is different, right? So when I differentiate e to the x, I get e to the x. But what happens when I differentiate 2 to the x? I do not get 2 to the x. So that's what we are focusing on right now. So two to the x, let me refresh your memory on one exponential. I'm thinking if I can use 2 to the x. Yes. So let's do that. Now, I'm thinking of changing the base. I have to change the base in order to prove this. So the answer is 2 to the x times natural log 2. But I don't want to just give you the answer, because you're going to ask, and rightfully so, why natural log 2? Okay, so I have to show you how to change the base formula, and we're not discussing natural log just yet. So I can't show you that at this moment. So we have to wait for the next section, and then we'll come back to this. They do not show a proof in your book. What they do, they just plug in numbers, and I don't want to do that.
Are we still going to do the ones with A?
Yes, yes, yes. So just leave it alone for a moment, and let's look at a couple of word problems, and then in the next section I'll explain how we get that. Okay, so let's look at a few word problems with the exponential, with base e. I don't see anything else just yet. Oh yes, I did see another one with another base. Okay, so let's take a look at either marginal supply. What I would like to look at, honestly, is the medication concentration. I was waiting for you to come in, and I said, okay, let's come up with an interesting problem. And I think that this will be interesting to you. So let's look at 91 on page 306. And then we can choose, please choose anything else you want. Medication concentration. The concentration C in parts per million. I take notes when I read. Of a medication in the body, T hours, so T in hours, time, of course. After ingestion is given by the function C of T equals 10 T squared e to negative T. So we take a medication. A lot of time and effort was put in this function. And they said, okay, if you take a medication right now, 4 hours, 10 hours, 3 hours, whatever, later, the concentration in the bloodstream 3 hours later will be 10, 3 squared e to negative 3. And the answer will be in parts per million. Good. Let's read on. Find the concentration after 0 hours, 1, 2, 3, and 10. So in part A, they want us to find C of 0, C of 1, 2, 3, and 10. Let's do that. We're not going to do that by hand, of course. I'm going to put the function in the graphing calculator. You can start if you'd like to put it in already. So C of 1, C of 2, C of 3, and C of 10. No one wants to do this 4 times. And I hope you will not even consider that. So in y equals, let's put in this function, clear what you have. So it's 10, it's x squared, and e. I will always put parentheses around the power like this, especially with a negative number, starting with a negative number. So this is what I recommend, 10 t squared minus e to negative t. And now we go to second and table. And I plug in 0. Of course, I'll get 0 because there was an x squared in there. And then 1, and then 2, and then 3, and then 10. So the concentration in parts per million, 0 seconds after we take the medication, is still 0. An hour later is 3.6, and 2 hours later is this, and according to the model. So at some point in time, I see what's happening. I'm cheating a little bit because I'm looking at this graph. So obviously from 0, it has an increasing and then decreasing towards 0. We hope that any medication we take will eventually be eliminated from our system, unless we take it every day, right? So we take medication, we're sick, we take a medication, an antibiotic, I hope not, but at some point in time, it should get out of your system if you stop taking it, right? Okay, so these are the answers. I'm going to copy them. C of 0, of course, is 0 in parts per million. C of 1 was 3.68. And then 5.41. And then 4.48. And 0.0454 after 10 hours. Okay, so I copied those numbers down for you. Part B. Sketch a graph of the function between 0 and 10. So in part B, for time between in the interval 0 to 10 hours. I'm not going to sketch the graph right this moment because I need some information. So in part C, find the rate of change of the concentration. So we are asked to find C prime of t, of course. And then in part D, find the max value of the concentration and the time it occurs. Of course, I need some information. I cannot just copy a graph from the graphing calculator, right? Okay, so let's find C prime of t. And here's the function. 10t squared e to negative t. Remember the constant, keep the constant outside, you make your life easier. First function prime. Perfect, times e to negative t. Plus t squared times e to a function. This is not e to plain t, is e to negative t. So it will be e to negative t multiplied by the derivative of negative t, which is excellent. Perfect. So this is t. Obviously, I will factor out what bothers me, which is e to negative t. Well, it doesn't bother me, but it's common in both. And then I have in brackets 2t minus t squared. So now when I'm trying to find what would be my next step if I want to graph this function? I have to find the critical numbers. Very good. So there is no critical number coming from this being undefined. Even if you change it into e to t, this will never be 0. We graphed it, if you remember. This will never be 0. Here's the graph. Let's go back to e to x. Or 2 to x is the same thing. It will never be 0. It's in open parentheses. It will never be 0. So this function is never undefined. But critical numbers can come from C prime being 0. When is a fraction 0? Only when? The numerator. So then 10 cannot be 0. So 2t minus t squared equals 0. I don't like the fact that it's not arranged in descending order. It has a negative leading coefficient. So then t minus 2 equals 0. And we have two options. 0 hours, yes. And then t equals 2 hours. So critical numbers 0 and 2. But will I know whether one of them gives a max or a min? I don't know. I have to study the sign of the derivative. So here is t. We're only interested between 0 and 10. And here is c prime of t. And we have 0, and we have 0 at 2. So now I have to find a number between 0 and 2, like 1, and plug in the derivative. So this is the derivative. I will not even consider these two. They are both positive. So please plug in 1 here and tell me the sign. Perfect. So now let's choose a number here like 5 and plug it in and tell me the sign, just the sign when you plug in 5. Perfect. So obviously, what happens at this point? What happens here? It's a maximum. Why? Because the derivative is increasing and then decreasing. So this is definitely a local max. So in order to answer the question, find the maximum value of the concentration and the time it occurs, we found when it occurs. How long after we take the medication? Yes, max concentration at t equals 2 hours. We know that it's guaranteed by the sign of the derivative. But how much is it? I have to find C of 2. But I already have it right here. We calculated a few minutes ago. 5.41. So C of 2, 5.41 parts per million. Max concentration. Any questions so far?
If we wanted to do multiple, this was based off of one dose. If
Yes.
we want to know multiple doses, it turns into a piecewise, correct?
I don't know. We have to look at the function. This function, that's a very good question. The concentration in parts per million of a medication in the body t hours after ingestion. So I'm assuming you're correct. Because it doesn't specify.
My curiosity,
But you're right. It has to be.
with the concentration, well, it's like at 2 hours, the max concentration's at 2 hours. So if you were to, but at the 10-hour mark, you have
It could
however
be.
much.
It could be a time release type of medication. Because it makes a little bit more sense.
Mhm.
So you take it, nothing really happens, till 3 or 4 hours later, it starts kicking in. Because it doesn't really make sense otherwise, in my opinion.
I was thinking like if at 10 hours you take another dose, at the following 2 hours for the maximum concentration still be higher at that point. And what would the concentration be?
That's a very good point. I don't know. I don't know because I don't know the medication they're using, and I have no idea whether after 10 hours, we know it's almost nothing, right? If you take it after 10 hours, it's probably going to use the same model. But if you take it, as you said, 2 hours later, I don't know how they would overlap. Oh, very good question. Very good question. I'm sorry I don't have a better answer.
That's okay.
Okay, very good. And it says interpret the meaning of the derivative in general. Well, we know how to interpret the meaning of the derivative. So one more time, the first question was find the concentration. Second question, which we did not finish, is sketch the graph. We will in a minute. Find the rate of change of the concentration. We did. Find the max value and where it occurs. We did. And part E, the last one before we go back to graph, interpret the meaning of the derivative. So what will we write for the interpretation of the meaning of the, or what is the meaning of the derivative? We will say it's the rate of change of concentration in the bloodstream with respect to time for this particular medication, for this particular model. The rate of change of concentration with respect to time.
Can you go back to the,
Yes.
rate of change on that problem?
Yes.
Please,
Yes,
what is that?
we're talking about C prime.
Okay. And, okay, that's just the derivative.
Yes, we set it equal to 0, and we found that it has two critical numbers. So these are the critical numbers.
Okay. And, how did you get two critical numbers?
I solved the quadratic equation. I set it equal to 0.